Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
Welcome. This is a talk on overload resolution. I am Barbara, and this is Ansel. Thank you so much for being here in person. It is fabulous to be around people again, and I'm sure pretty much everybody feels the exact same way. Let's get going. Overload resolution is a really large topic. And our intent, even though this is a back to the basics talk, we're going to start with the fundamentals, but then we are going to progress all the way through the topic. So if you were thinking we're just going to do the basics, we're taking it all the way today. What's very interesting about overload resolution is that we've talked to certain programmers that say, well, I don't like overload resolution, I'm not going to use it. But if you're using C++, which I assume you are, and if you're using something as simple as std string, you are actually already using overload resolution through implicit conversions. And we're going to talk about that a bit more. The other thing is, you've probably had a few compile errors. And some of those errors probably have messages which relate to overload resolution. So if you think you weren't using it, you are. But now we're going to teach you how to read the error messages and what it means and how to use it effectively. Before we get started with the talk, we'd like to just briefly tell you who we are and why we're doing this talk. Ansel and I are the co-founders of the CopperSpice project. CopperSpice is a set of cross-platform GUI libraries. And you can use this with any C++ application. Doxypress is an application that uses CopperSpice, and it is available for documentation. It works with C++, but it also works with many other languages. And there's various outputs you can go to. Obviously, the most prevalent would be HTML. We use Doxypress to document every one of our libraries. CSString, CSSignal, and CSLibguarded. These are three standalone libraries. So if you're like, well, I'm not sure I want to use CopperSpice, but I would really like to use CSString, feel free. You don't have to be using CopperSpice. But CSString, Signal, and LibGuarded are ones that we actually use in the core library for CopperSpice. And as you can see, CSString supports UTF-8 and UTF-16. And this is done through policy classes. So if you need UTF-8 support now, it is pretty much a drop-in replacement for std string. If there's other encodings you need, you can always add them. We would appreciate if you would upstream them to us, and we'll just put them in the library. CSSignal is a standalone library for thread-aware signal slot delivery. So if you really need signals and slots, which many people do, and that's all you want, you just link your C++ application with CSSignal. Ansel is the main author of LibGuarded. And it is a library for accessing shared data. So if you're a multi-threading programmer and you are using mutexes or locks, you want to be using CSLibguarded because it associates your mutexes and locks with your data. If you have questions about any of these libraries, please feel free to talk to us a bit later. But what's really important is everything we do, all of these libraries and applications, everything's open source. Everything's free. And it's available on GitHub. And you are free to use any piece of anything you want.
So as we start talking about overload resolution, we need to first look at some terminology. And we want to distinguish between some similar terms that are actually completely different. People talk a lot about overloads and overrides. And in order to understand the difference, we need to back up and look at the term polymorphism, which literally means something which has many forms. In computer science, we use this term when there are two or more possibilities for some choice that's being made. In C++, compile time polymorphism occurs when you have function, method, or constructor overloading. And this is where the correct function to be invoked is chosen based on the data types that are available to the compiler at compile time. Runtime polymorphism occurs when you override a method. And this involves invoking the correct method based on the runtime type of the object. These terms sound very similar and they're often confused, but they're very different in their application. So I mentioned function, method, or constructor overloading. And for the remainder of this talk, we're going to just say function overloading because the same rules apply almost universally. This occurs when you have multiple declarations which have different signatures. And this is the main topic for this presentation. Method overriding means that you have inheritance in the design of your program. So you have some method in the child class that has the same name as a method in the base class. So you might have a class fruit and a class apple, and both of them have a method called can you eat the peel? This sort of programming is more of the classical object-oriented design technique, and this involves virtual methods and method overriding. This is completely unrelated to the subject of overload resolution. And then operator overloading is another commonly confused term. This is where a different operation will be invoked for a specific operator given the data types of the data that you're working on. So as an example, if you declare a method called operator plus, and that's actually the name of it. Operator overloading always involves a name that starts with the word operator followed by a symbol, like a plus sign. So your operator plus might be adding two numbers or concatenating two strings, depending upon the data types you're working with. The mechanism of operator overloading uses overload resolution to find the appropriate implementation for the operator that you're using. So as we go through this and you get a better understanding of overload resolution itself, you will also gain the ability to use operator overloading effectively and understand the decisions it makes.
So why is overload resolution required? Well, an overload occurs when two or more functions have the same name and are all visible where the call is being made. So we have a small example here of do function. In one case, it's passing, quote, mountain. In the other case, a 17. But we're using the name do function. If we didn't have overload resolution, we would actually have to have everything with a different name. That probably works on do function string or do function int or do function bool. But then it's going to get really messy really fast. Do function pair int string. I'm assuming that that would be a pair of an int string. Then I need another name for do function pair string int. Do function function pointer would be really awkward. So we have this great thing of overload resolution, so we don't have to do this. We can just use the name do function, and we can let the compiler decide which is the right overload to call.
So how do we actually declare overloads? Well, as I mentioned, it applies to free functions, methods, and constructors. We're going to refer to all of these as functions. Two function declarations are overloads of each other when they have the exact same name, they're visible from the same scope, they have a different set of parameter types, so you can think of this as having a different signature. The order in which you declare overloaded functions is not meaningful. So it doesn't pick based on what order the compiler saw them in your file. And every overload that's visible to the caller can potentially be called. This may include overloads that you wrote and overloads that you did not.
So here's our first real example. So we have do thing. And in main, we're calling do thing with 42 on the first line and do thing 42, 3.14. There's nothing special about this particular example. The first one is going to call overload 1. The second one is going to call overload 2. And this happens because the parameters match. It's very clear. This does exactly what you would expect. This is the easy case.
So what is overload resolution itself? Overload resolution is the process of choosing the most appropriate overload. The compiler must do this, and it must do this at compile time. And it can only consider two pieces of information in this process. It can consider the data types of the arguments you passed and the data types that each declaration is defined to receive. It cannot look at the actual values. It can only look at data types. And if the compiler can't choose one specific overload as part of the overload resolution process, then the function call is ambiguous and you get a compile error. An additional complexity to the overload resolution process is the fact that template functions and methods can participate in overload resolution. And if two overloads are considered equal, the non-template version will be preferred over the template version.
So if two functions, they only differ in the return type, this actually doesn't compile. Since the return value is optional and you don't have to use it, the compiler actually treats this as you have redeclared the same function. So this doesn't actually work. They have to differ in more than the return type. If two functions, if there are default arguments, so let's say you have two overloads and they both declare a bool and one is defined as true and false, this is also a problem and it won't compile. There has to be something more distinctive in the signature for it to actually be an overload. And two methods with the exact same signature, where one is marked static, that also doesn't work because it is not actually an overload. If we have any questions, please feel free to ask anytime. And for those of you online, if you do have a question, we do have somebody moderating, and we can also address those questions at any time. Okay.
So when you have overloaded functions, the compiler needs to to have some mechanism for figuring out which function to call. And in most cases, this does what you think it should. But it can get really complicated really fast because data type conversions can be considered, and some of them are surprising in their behavior. If you have pointers and references involved in the call, it may not resolve the way you initially think it should. Template functions can do strange things when their arguments are being deduced. And one of the most frustrating errors in this area is when the wrong overload is selected according to what you think the compiler should be doing. It can be very hard to understand and debug this. But as a C++ programmer, you really need to be able to do this because at some point in your career, it will occur and you will need to be able to figure out why the compiler is doing what it's doing.
So when should you use overloads versus a template? This is a really interesting question. And I hope everybody's actually thought about this. Because again, some people say, well, I don't want to use templates, they're scary. Or I don't understand overloads. But the purpose of using an overload set or using a template, it has a distinct usage.
One of the best ways to think about this is you should use overloaded functions when the implementation is going to be different depending upon the data types that it's operating on. And you'll see an example for this in the standard library in the constructors for std_string. There's a constructor that accepts a const character star and it copies the data into a new allocated string. There's another constructor, the move constructor, that takes an std string by rValue reference and moves the data out of that object. There's another constructor that takes a size type, an integer type number, and a character, and constructs a string with that many copies of the given character. These are all in the same class. They all have the same name because they're all constructors, and constructors are named the same as the class. But they are implemented completely differently because they do completely different things. Templates are a better choice when the body of the function does the same thing, no matter what data type you're operating on. So as an example, consider std sort. It takes a begin and an end iterator, and it does the same thing. It sorts the data regardless of the type of container or the type of element that you're passing to it. So this is the stereotypical example for when you would want to use a template, when the behavior and the implementation works for all T.
So as we're starting to really get into what is overload resolution, we wanted to mention the C++ standard. If you're using C++ 17, the definition of overload resolution is in clause 16. It's about 32 pages. If you happen to be using 20, we thought we would throw this in. It's in clause 12, 35 pages. But for those of you that may not have actually looked at those standards yet, and looking at 20, they changed the page size and they reduced the font. So you can't quite compare 32 to 35. They've actually added a lot more information. But if we're looking at the other things like name lookup and declarations, this actually comprises probably 40% of the C++ standard. And now you're saying, why do I need to know user-defined conversions or S-fine? Because it is part of the overload resolution process. And we're going to be going into how each one of these parts plays into the overload resolution system. But it's really important to understand that's why overload resolution requires knowing so much about the standard.
So our overall goal for this talk is to give you enough information about how the overload resolution process works that you can find what more information you need in order to debug a particular problem. Because to cover the topic in full detail would be a long workshop. Now, before we can even start doing overload resolution, the compiler has to do something called name lookup. It has to find all the things with the given name that it could possibly be calling at the location where you're making a function call. So it's just the process of finding every function declaration which is visible from the current scope with the given name, which sounds pretty simple, except it may have to look in quite a few namespaces, like the one you're in, maybe the class you're in, going all the way up to the global namespace. It may also involve argument-dependent lookup, which means if you're calling my function, and one of the arguments you're passing to it is an std string, it will look in the namespace std for my function, even though you didn't qualify that or import that namespace. So the list of namespaces that name lookup will cover can be quite large. Template functions, if any of them are found during this process, may require template argument deduction, where the compiler looks at it and says, what should I deduce the t's to in this call to do the best job of instantiating this template? Once the compiler runs through that entire process, we now have a list of visible function declarations. We call that the overload set for this particular call. And it's going to be different for every call because the scope may be different and the arguments may be different.
So now we get into the actual overload resolution process. And the very first step is we take this overload set and it gets put into a list of candidates. The second step, yes, I'm sorry, we have a question.
Are conversions and promotions involved in template argument deduction? Can you say this for finding the overload set?
The question was about whether anything else plays into assembling the overload set, and it does not. In compiling, the compiler takes everything it can see, puts it in the overload set, and then creates the candidate list. So the candidate list is everything that's available. Nothing else has happened at that point. In the second step, that's where the compiler then says, I'm going to remove anything that's invalid. And if you're looking at the standard, it refers to these as not viable.
And this is a useful term to know since this will show up in compiler error messages frequently, the term not viable.
So at this point, all we have is everything available, and we've trimmed it down to what's not viable. So the question is, what makes something not viable or invalid?
And there's two possible reasons that a candidate could be thrown out at this step. One of them is that the number of arguments you're passing in the function call can't possibly match the declaration that it's looking at. So if you're passing too many arguments for the given declaration, that's always considered invalid. That's no way that will work. If you're passing fewer arguments, that's usually invalid. But of course, default arguments can be declared in the function declaration. And so those are optional. So passing fewer arguments than the given declaration may be valid. So you can see on this example, we're calling doThing and we're passing 38. Candidate A is not viable because we're passing too many arguments for candidate A. But candidate B is viable because we're passing too few arguments, but the excess arguments are defaulted in the declaration. So in this case, candidate B will be chosen, as you would expect.
Go ahead.
The other reason why a candidate might not be viable is if there's no way for the compiler to convert the arguments that you're passing, those data types, to the declaration what the function expects, even while it considers implicit conversions. So in this case, we're still calling doThing and passing 38. We now have 3 candidates. We're still passing too many arguments for candidate A, so it's invalid. We're passing the correct number of arguments for candidate B. It's valid. Candidate C, we're passing the correct number of arguments. However, there is no conversion available to convert an int to an std string. So candidate C is invalid and not viable for the second reason. So still, candidate B will be chosen as you would intuitively expect.
Yes, we have a question.
So I think you said a default argument value won't change things, but if you had another candidate that just took a single int parameter, not an int and a bool, would that still be resolvable?
Repeat the question.
So I think the question was if we added another candidate that only took an int and not a bool.
Your last example showed an int and a bool where the bool was the default parameter.
This one.
Yes.
So if you had a third one there where it just took an int, it didn't have a second parameter, is that still a unique signature?
If you had another overload here that just took an int and did not have a second parameter, that's actually a compile error because those cannot be distinguished for some sets of calls. So that doesn't form a valid overload declaration. Does that answer your question? Yes.
I think we have, was that an online question?
Yes, we have an online question. So the question is, if we passed a float, would it be implicitly converted? What if we had a float declaration? Would it pick the correct overload?
Can we please defer that question for about 3 more slides? If you can hang on with us.
Question.
It's an excellent question, and we will answer it. Okay. So going over this overload process. So we created the candidate list, and then we removed anything that was invalid. The next thing we're going to do is we need to rank the remaining candidates. And this is where the crux of everything happens, is in the ranking. If we're actually at this point, and there is one candidate that is the highest ranking, or there's only one in the candidate list, we're done. And we have a winner, and that winner gets called. There is one more step that then will happen, and that's if we have 2 candidates that are both the highest ranking, we enter what's called a tiebreaker.
And this step in the middle of ranking the remaining candidates, this is where most of the complexity of overload resolution comes from. And this process is what uses a great amount of the standard to try to decipher which one to choose. But before we can even look at how the compiler ranks things, we need to step back to the fundamental idea of type conversions, because they're crucial in this process. So type conversions are any time you convert a value from one data type to another. And we do this all the time. We convert ints to floats, string literals to pointers, type X to type Y. It happens all the time. There's many conversions available in the standard, and there's a bunch more that may be available depending upon your code base. So in this example, we have a straightforward thing where we're calling doThing and we're passing 38. The data type of 38, it's a literal. We're passing an int. And since we only have one declaration of doThing that is declared to receive a float, in the call, 38 will be converted to a float using implicit conversion. And I believe we have a question from online.
The question is, we've noted that at times the conversion the compiler decides is different than expected, that therefore overrides to an unexpected overload. Is there any way for that to be flagged as ambiguous? And perhaps maybe this is what you will address later.
We are going to address it, but it's an excellent question. And again, thank you to our online people for asking questions. Bear with us. We have a long way to go, so we're going to actually...
That turns out to be a very deep question.
A very deep
we
question.
Will get there.
We will make sure to answer it.
So we use implicit conversions quite frequently. You can't even see them. In this first example, we have an array of characters, and we're taking the first character out of that array and assigning it to an int. It's being implicitly converted to an int, so we'll get the number 65, assuming you're on an ASCII system. There's also explicit conversions, and these are things like static cast, dynamic cast, or a C-style cast. And there's another type of explicit conversion called a functional cast, where you use the name of the data type as if it were a function to do the conversion. Some people call this calling a constructor. That's not actually the way the standard looks at it, and it's kind of incorrect terminology. The correct term is functional cast.
So we started talking about the ranking. And in the ranking, we need to start looking at standard conversions. And we have 5 of them. These are the first 3. It seems a little odd, but an exact match is considered no conversion, but it is actually the first standard conversion. The second one is L transformations, and then the third one is qualification adjustments. Now, we've assembled this all from the standard. You don't have to memorize all of this, but you have to understand that there is a ranking. The 4th and the 5th one are more interesting to us. 4 is the numeric promotions, and 5 is conversions. So all 5 of these are part of the standard conversions. And again, something that's a 4 is better than a 5. So you at some point, you may need to know, where is my ranking? So we're going to do that with some examples as we go on.
So qualification adjustments, as we saw, was category 3. And the qualification conversions are what it's called when the compiler adds const or volatile to a pointer data type. So in this example, we are passing my string, which is a variable we've declared. It's a pointer to an std string. We have 2 overloads in the candidate set. One of them takes an argument that is a pointer to a const std string. One of them takes an argument that's a pointer to an std string. Since there is a qualification conversion available, this is an implicit conversion the compiler can consider. Both of these candidates are valid. However, the second one is an exact match. Candidate B is an exact match for the passed parameters. Candidate A is not. So although they're both viable, candidate B will be chosen.
Can you contrast this with a const pointer to a std string?
Contrast this with a const pointer to a...
With a const pointer to a std string.
If you have a const pointer that is actually not relevant in the overload process because the const is not considered as part of the data type.
Let's take a look at example 2. This is our first quiz, and we're going to try to do these pretty quickly if we can. So we have main, and do thing, we are passing a 42. Which one gets called? Overload A or overload B? And again, if you're online and you want to vote, please do so. We have a moderator here who can tell us. Somebody want to take a stab at this before I call on somebody?
A show of hands.
Show of hands.
Who thinks A? Who's for A? Okay. Who's
for B?
Okay. The consensus in the room seems to be B.
Anything from online, or we'll just...
I think the consensus is B.
So mostly B.
Okay.
And I also have a online question that was about implicit conversions. The question was, is there something you can do to prevent implicit conversions in determining overload resolution?
We will address that. We will address what you can do with implicit conversions. Thank you for bearing with us on some of these questions. So it seems like the consensus of this is that most people believe it is B.
Well, you're in good company because that's
exactly what we thought.
What we thought too.
And then we had to read the standard for quite a long time. That is not the right answer.
So
it's ambiguous.
This is our first surprising result of overload resolution. Let's dig a little bit into the standard and find out why. So category 4 of the ranked conversions is integral promotion. And these are things like short to int, unsigned short to unsigned int. And recall, integral promotion is a higher rank than integral conversion. So the promotions are preferred. There's a lot of integral promotions, but they are defined explicitly in the standard. They are laid out of what constitutes a valid conversion. Floating point promotions are even easier. There's one, float to double. That's it. On the other hand, integral conversions are any conversion between two integer data types, one A and B, where the standard didn't explicitly say it's an integral promotion. And if you go back to here, you'll notice something odd about the promotions we've chosen. The basic rule can be summed up as all integral data types smaller than an int can be promoted to an int. There are no promotions to long or long. Promotions stop at int, essentially.
And this was exactly what we thought, is that taking from an int to a long, well, we'll just promote it a little longer. It's not what the standard says. We've just saved you 6 hours. Because it turns out it's not a promotion. It's a conversion. So in the example we just showed, the reason why it's ambiguous is because you could convert to a char or to a long. So
And
it's
they're
ambiguous.
equivalent.
So
Now that doesn't mean you can't do an integral conversion. Because in this example, we are calling count and passing 42, which is an integer literal, it's an int. But we only have one overload that accepts a long. That's perfectly fine. This overload is a valid candidate. And so there will be an integral conversion that occurs. There's no ambiguity here because there's only one candidate.
So we started out in the ranking saying that there were 5 for standard conversions. Then there are 2 others that take place in the ranking. The next one we're adding is the user-defined conversion, which happens more than you think. And then the ellipsis conversion, which probably happens less than you think.
So let's look at these in a little more detail. So user-defined conversions are ranked lower than any of the standard conversions. And the definition is a little bit surprising. A user-defined conversion is an implicit conversion to or from any class data type. That means the class declaration could be located anywhere. Even if the class that's being converted to is in the standard library, it's considered a user-defined conversion. So in this call, we're passing a const character star message to our function showMessage. ShowMessage is declared to receive an std string. This is a valid candidate because there is a constructor for std string that can be used to do this implicit conversion. But it is a user-defined conversion. It's worse than any other standard conversion. If we were to add an overload that, say, took a void star, that would win, which is unfortunate. But that's the way the rules of the ranking are defined.
So as we mentioned, if we're ending up at a place where we have two that are the exact highest, then we need a tiebreaker. And tiebreakers aren't used all that often, but they do come into place. You need to know about them. And when you have a template and a non-template candidate tied for first, the non-template is selected. And that's really important to know. What's also important, and I think this addresses possibly one of the online questions, is with implicit conversions, what we're looking at is how many steps it takes. Because if something takes fewer steps, that's what's going to win. And we do have some examples that will show that. And if there's no best match and it can't be resolved in a tiebreaker, you will get a compile error. And then you need to resolve that.
Define steps in presence of multiple arguments, or is it going to be later?
Yes, we are going to find the steps. We do have an example that will address exactly that question. Yes. Where does ellipsis fit?
If you see the full list of conversions, the question was where does ellipsis fit? It is below all user-defined conversions.
It is the worst.
As it should be.
As it should be, yes. Okay, go on more.
There's a new tiebreaker rule that was added in C++20. This is where concepts play into the overload resolution process. So if you're not familiar with concepts, it's a new feature in C++20 that allows you to specify a concept for a template to constrain the T. So it limits the set of data types that are allowed to be used with that template. Now, applying a constraint to a template doesn't really change how it participates in the overload resolution process all that much. What happens is at the end of the overload resolution process, if there's a tie, then there's a tiebreaker rule that says the more constrained template is preferred over a less constrained template. And this gives concepts a lot of usefulness in resolving ties in overload resolution in C++20. We have a question.
Oh, we have an online question.
The question is, just to be sure, even though stud string is part of the standard library, converting from const char star to stud string is considered a user-defined conversion?
Yes.
Yes.
Yes, it is considered because std string is a class in the standard library, which means if you're using a third-party library like CopperSpice, you may need to consult the documentation to know what implicit conversions we have as well. And this is also going to be if it's an internal application you're using. So you need to be aware of the API. Let's take a look at example 4.
So here we have do thing for it. We have two declarations for it. We're passing the value 42. Which overload will be called? Show of hands, anybody going for A?
Candidate A. Ooh, most of the room.
How many people?
Candidate B. The other half of the room. Probably have some online people taking a look, typing really fast for A or B. Do we
difficult to tell, but I think there might be a slight edge to A.
to A?
Okay. So mixed results.
Mixed
both in the
results
room
on A and
online.
B. Okay. Let's take a look. Candidate B wins.
And the reason for this is, despite the fact that we said a non-template function is preferred over a template function, that's only if there's a tie. And in this case, we're passing 42, which is an int. During template argument deduction, the compiler deduces T to be an int, which means that candidate B is an exact match for the data type, so it wins the ranking, and there's no need for the tiebreakers. This is a reason why you should avoid having functions and template functions in the same overload set as a general rule, because the templates can deduce to be an exact match a lot. And we'll have more examples of this.
So when we're looking at the candidate list, how do you resolve an ambiguous function call? And what happens if all of a sudden you say, I have my candidate list, this one should win, and it doesn't? And you're sitting there tearing your hair out. Well, there are some tricks you can do. You can add or remove an overload. You can look at the candidate list, and you're going to need to get really good at looking at that output, no matter how long it is. And it will say candidate list, and it will list everything.
And if you're lucky, it will give you the reasons why each candidate was considered invalid. That's really useful when your compiler gives you that.
But not always. You can also mark a constructor explicit to prevent an implicit conversion. And this was something that was asked, I believe, from the online. So if you're looking at your candidate list and you're like, I think it's hitting this one, just temporarily mark something explicit if it's in your code base or you have access to it. Mark it explicit. That will throw it out of the candidate list. That's not the final solution. But this is the time that you're trying to figure out, why did this particular candidate get picked? So this is one of the tricks you can use.
And in general, people forget to mark constructors explicit anyway. You often don't want constructors to be used as implicit conversions, so pay attention to that when you're defining your classes. You can also eliminate, if there are any templates in the candidate set, you can eliminate them using asFine. And asFine actually works through the overload resolution process by discarding candidates when it's discovered that they can't be used as valid candidates. This is also something you can do by adding concepts if you're in C++20. Whoops. You can also convert the data types that you're passing before the call, so you can influence the input to the overload resolution process by using an explicit conversion. You could static cast some of the data that you're passing, or explicitly construct an object to change what is considered during overload resolution.
So example 5 is pretty simple. All we're really showing you here is that if you get an error that says no matching function for call, then you didn't have any viable candidates. So this is something to be aware of when you're reading compile errors. And this is why we mentioned that you're using overload resolution even when you don't know it. So now you understand what this error means, and it means I didn't have anything to call. Your candidate list is not large enough.
The really frustrating situation is when the compiler does find a best match, and it does call one overload, but it's not what you wanted it to call. It's really hard to debug this because there's no way to ask the compiler, why did you do that? Why did you think that was the best option?
A verbose listing would be really nice. If it would say, here are the 6 candidates, here's what I chose, here's what I didn't choose, here's why. I suspect at some point, maybe compilers will get a little better with that. They're not there yet. So you're going to have to do the reading, and you're going to have to decipher.
Until that happens, one of the best strategies is, now that you understand how overload resolution looks at the candidates, you can add another candidate that will force the call to be ambiguous, and then look at the error message to see what it thought about all the various candidates. You can also try changing the data type of some passed argument to get it to be a better match for the function you think ought to be called.
Now we begin the fun round. Example 6. If you look at A and B, in do thing A and do thing B, we're passing 4, 5, 6. So that part's the same. We saved you some reading. And in A, we have overload 1 and 2, and in B, we have 3 and 4. These are not connected examples. We're just doing 2 at the same time for a specific reason. And this is where we absolutely encourage you to participate. This is the fun round. Really look at this. Which overload will be picked? And if you would like to tell us your logic, just pipe up and Fedor will start talking. See how I just point on people? I know we're playing the Jeopardy theme right now.
Can I have a show of hands? Who thinks number 1 will get called in the first example? Okay, what about number 2?
Nobody.
Okay, so the consensus is 1, all right? What about 3?
For example, B, it's a 3.
And what about 4? Any sort of consensus online?
For the first one, results are mixed. For the second one, I think people prefer 3.
Okay.
If there's anybody that wants to speak up and say a question, what they think before we tell you the answer, we're happy to entertain here. No volunteers. Oh, somebody in the back, yes.
Is it 1 and 3 because there are fewer conversions required?
Is it 1 and 3?
1 and 3.
Because there are fewer conversions.
Why would there
required?
be fewer conversions on 1?
Because they're all integral, they're all integral.
It would be nice if it worked that way.
Actually, it used to,
It doesn't.
it used to work that way.
Fedora says it used to work.
It may
that
have
way.
worked that way. We are basing most of this on 17, but I believe nothing would change in 14 or 11 or 20.
So let's find out what the compiler actually does.
Example A is ambiguous. In B, 3 wins.
The reasoning for this is a little bit subtle, and it's because multiple arguments are considered one at a time in the overload resolution process. So if you look at example A, we look at the first argument. Overload 1 loses, so it can't be the best match. Then if we look at the second argument, overload 2 loses, so it can't be the best match. So there's no candidate in first place. So the call is ambiguous.
It doesn't look at, the idea, the intuitive first approach is we're doing exact matches or conversions. So the idea of overload 1 is, well, it wins twice, and overload 3 wins once. But that's not how the compiler looks at it. It does go across and tries to decide who wins. And as Ansel was saying, once we get to the second argument, there's no clear winner.
On the other hand, on example B, if we look at the first argument, they're equivalent. So they could both be the best match. When we look at the second argument, overload 3 wins. So it remains in consideration. And then we look at the third argument, they are again tied. So overload 3 wins because it won at least one argument and was no worse on the others. This is very useful to know when you have multiple parameters. Question?
It should do that argument by argument with the tie break as well, so like it doesn't wait till the end.
The question is that argument by argument with the tiebreaker? No, the argument by argument processing happens during the ranking process.
Okay.
Then the tiebreakers run.
And this was actually decided in ranking, in the ranking process. Great question.
Excellent question.
Great question.
Let's look at another example.
So to help you walk through this, again, we've got a D.
question.
Oh, we have an online
sorry,
question. I'm sorry.
On the previous slide,
Yes.
what is considered a better match, a defaulted argument or no argument?
What is considered?
What is considered a better match, a defaulted argument or no argument? You actually have to look at the standard on that one.
Okay, and there's an additional question. Why would the compiler stop looking at the argument list at the second argument, having found it ambiguous, without continuing to later parameters that might resolve the ambiguity?
You're talking about example A. And in example A, the second one wins, overload 2 wins, and then overload 1 wins. We have no clear winner at that point because no one is actually better.
You can think of it like in some sports, there's no such thing as a tie. It's just a double loss. So there's no winner once you look at the second argument. There's no reason to continue because no overload can win at that point.
And this is a subtlety of overload resolution. That's why we put the example in.
Let's look at the next example.
Sorry, there's one more question that came in. What if argument 3 in overload 4 was an int?
If argument 3 in overload 4 was an int, then you would have the same double loss situation as in example A. It would be the same situation because both would lose at least one argument, and therefore neither of them could be the best match.
So back to example 7. So again, in main, notice that in example D, we've assigned 42, so we have an L value. In example E, we're passing 42, which is an R value. So we've now given you all the information. So now we're looking at the same type of thing. Is in example D, are we looking at overload 1 or 2? And in E, 3 or 4?
Who is for overload 1? 2? 3?
Oh, we do have a question? The question was, is this compiler dependent? And no. We've gotten the same results on every compiler we tested, and we did run most of this with 14 and 17, but we have not found any differences. If there's a difference in 20, we have somebody here who will pipe up and let us know. But so far, I haven't seen that happen.
This area is well defined.
Is well defined.
If your compiler doesn't give you the same answer, file a bug with the vendor.
Yes. Okay, so back on D, overload 1, because I already forgot how many people. We have a couple. Overload 2, you have to vote?
No, you don't.
I'm sorry, somebody's saying ambiguous, okay? So we have a couple people on ambiguous. What about on E? Overload 3, 1 person.
Overload 4?
Lots of
Most
people.
Okay.
Okay.
Let's look at the answers. So we had an existence proof of several people who were correct in this. For the first example, it's ambiguous. And the reason being, we're passing x, which is an int. It's an L value. And we have 2 overloads, one which accepts an L value reference to an int, and one which accepts an int by value. Binding a value to a reference is not considered to be a conversion. So these are both exact matches. They have the same ranking, and there's no tiebreaker that will resolve this. So this is ambiguous. In the second case, we have an R value that's an int. You cannot bind an R value to an L value reference. So overload 3 actually isn't a valid candidate. So 4 wins because it's the only remaining candidate.
Non-const L value reference.
Thank you. Non-const L value references cannot bind to. Yes.
Which is what ours was, yes. Let's try it again on the exact same main on F and G. But we have changed the overload set. Added a few more ampersands.
So now each case, we have one candidate that accepts a non-const L value reference to an int, and one candidate which accepts a non-const R value reference to an int.
For F?
1, 2.
Ambiguous? A couple of those too. Everybody's getting scared.
For 3?
No. On G, overload 3?
Overload 3. Overload 4. Okay.
Okay, ambiguous? Because we keep doing that to you. Okay, let's take a look at the answers.
So in this example, for F, overload 1 wins because it is not valid to bind an L value to an R value reference. For the second example, do thing G, overload 4 wins for the exact reverse reason. It's not valid to bind an R value to an L value reference candidate. If you understand this, you understand most of what you're dealing with when doing move semantics in C++ 11 or later. Question?
To ensure, you said not valid, not ranked lower.
The question was,
excellent
you said
question.
Not valid, not ranked lower. That's correct. So for example, overload 2 is not a valid candidate. The way the compiler looks at it is there's no conversion from an L value of type int to an R value reference of type int. So it's just not a valid candidate. It's thrown out at the second step.
I think we have an online question.
The question is, why 1 in F and why not 1 in D?
Why 1 in F and why not 1 in D? Because in
D,
the L value is valid for both candidates, and there's no rule that distinguishes them. In F, only overload 1 is a valid candidate.
Is viable.
That
Yeah,
is a
is viable
viable
candidate.
So there's no need for ranking. If we got to the ranking step, this would be ambiguous, but we don't.
Another question from online? Yes.
The question is, can you give examples when there would be an L value to R value conversion?
And
Can we give examples of when there would be an L value to R value conversion? That one is actually misnamed in the standard. It's very confusing, and we don't have any examples of that in the slide deck. It comes up in the in dealing with temporaries occasionally.
I think we have time for the bonus round.
I think we do.
Because you should always have a bonus round. So in this, do thing 9. This is an L value reference to an int. If you're not familiar with the ... which is absolutely fine, this is the C-style var args. So those are our candidates. Now we have a structure, myStruct, and that is a bit field. Not something everybody uses, but it's a bit field of 5 bits being stored in an int.
Then in main, we declare an object of our structure, and we pass the bit field to do thing 9. And the compiler has to choose which overload to use. Who thinks overload 1? Anybody for overload 2? Okay, a couple of people going for overload 2.
Should we offer ambiguous just in case?
Yeah, does anybody think ambiguous?
No, no ambiguouses.
No? Nobody's
So it
ambiguous?
sounds like overload 1 got a few votes for the people who weren't voting.
So definitely mixed results in the room. Well, let's find out what the compiler actually does. Overload 1 wins.
Fantastic.
One of the interesting quirks of C++ is that bit field is not a type. Bit fields do not participate in the type system. So for purposes of overload resolution, the compiler looks at this as you're passing an L value of data type int. The first overload is an exact match, so it wins.
Hang
However,
on.
It doesn't compile because you can't bind an L value reference to a bit field. So the function call fails. So this is a case where the compiler chose an overload where the call doesn't compile over one where the call would. Because if it had chosen the C-style var args, it would have copied the int. And that would be legal.
We think the moral is bit fields maybe aren't good or var args, we're not sure.
Maybe just avoid both.
Both, just a bit. So this was the bonus round. It was fairly tricky. What is noticeable, and we put it right on the slide so you don't miss it.
If you add an overload that takes a const int reference, which would compile, it still doesn't change the result because it's not a better match than the one that takes an L value reference to an int.
Just really hard code to figure out.
But it's not the worst one, is it?
It's worse because
It's
it
worse.
requires a qualification conversion.
Yeah. It's a lower ranking. Yeah.
Yeah.
So no matter what you do, it doesn't work.
So the takeaway from this is overload resolution is a large and complex topic.
You really need to understand a lot of the standard. I mean, we've talked about L values, R values. We've talked about S fine A. You don't necessarily need concepts unless you do move to 20, but you need a lot of the standard. Learn the difference between promotions and conversions. That is a part I would say, just take that to memory. And if you're not sure, know where to look it up. Keep in mind, promotions are very small.
You should really try to avoid mixing overloaded functions with templates. We've talked about that a couple of times and shown you some examples of why. And debugging ambiguous overloads can be very frustrating. Accept that as part of C++. It is work to figure out how this process reached the result that it did.
We'd like to mention that we have a YouTube channel, and we have several other videos on this YouTube channel, but we're pointing these out. Since this is a Back to the Basics talk, the videos that we've listed here, especially these first 3 of modern C++, they are our most watched videos. And we encourage you to watch them, whether you've been using C++ for a week or 20 years. Understanding value categories and move semantics. We used it the whole time during this talk. We also did a keynote at CppCon this year. We'd like to suggest you watch it. It's a very different talk because it is about being a programmer and programming like you mean it. And do you show up like you mean it? And we encourage you to watch that. Then go ahead and watch the other 65 videos. You've got some spare time. This is it keeps disappearing. So these are some of the other videos. All of our YouTube videos are about 10 to 15 minutes. And again, it's both of us talking, and there's probably something of value. If you're a multi-threaded person, there's plenty. If you don't know concepts, there's something to watch. So again, we're CopperSpice. Everything we do is open source. We've added 2 other libraries to our litany of stuff. A crypto library was released earlier this year. Please give us your feedback. We have CS Paint. If you're not sure of what's in CopperSpice and you want to take a look at it, Kitchen Sink is a demo program, and you can actually, we have it compiled. It's on our download site. Pretty much, we're on 16 different platforms. I'm sure we have a binary for your platform with over 30 demos. If you're like me and you want a very lightweight editor, Diamond is something you may want to take a look at. All of these use CopperSpice.
If you want more information about anything we do, go to our website, contact us, find us throughout the remainder of the conference, and I believe that's
our talk. Thank you very much for attending. If there's any questions, anything from online. Yes, we have a question.
I had a question about example 8.
Example 8.
It had an integer, it had an int ref in there. What if the int ref was a t ref with a template?
That's a good question.
Universal reference.
Yeah, it's
Yeah.
that's a forwarding reference, which means then it should deduce in that call to L value reference to int, which means it's an ambiguous overload, which then means the first one would win during tiebreakers because the second one is a template.
Sorry, I was referring to example G.
Oh, to G. Okay.
Since you can, we talked about.
In example G,
Yes.
if which one, 3 or 4 was a T ampersand ampersand.
Was a T ref.
So if 4 was a T ampersand ampersand, then it would deduce to int ampersand ampersand, and it would win.
Which it does
Because it's
anyway.
the only viable candidate.
Yes.
If one is providing a library for you, does it make sense to have, let's say, a push function that takes a constant L value ref, an R value ref, and a pass by value, or should we just pick the first 2 or?
So this is about so you're asking how should you design your API?
In general, in a case like that, you'd probably prefer to just have one that takes by value. Because then that will do the right thing for data types that are copy only, data types that are move only, and you don't have to deal with multiple overloads.
I think that's one of the odd parts with move semantics is then everybody thinks everything needs to be an L value and an R value. And there's a lot of times you still want your parameters to just be a value. And that's something to consider.
Thank you very much.
Thank you.